Can you show the first equation when you say that we know the physics, the first differential equation that you showed at the very beginning when you start the So the question goes in terms that it's a curious, that's one. How old are these equations? I mean, Navier-Stokes is from 1825, 1850 or something like that.
Conservation of mass, momentum, energy, and chemical species. Yeah.
So my point is, people invented, designed, discovered these equations without having computing science or computing power in mind. Have anyone tried to think and readapt these algorithms in terms that saving power, reduce computation? Because you are just this is the equation, this is how physics work, this is how nature is, and we go from there. You put computing on top of that.
I don't know that that's... So there...
I mean, is this something worth thinking about?
Incredible, right? If you think back to the sort of the timeline chart, Ford simulations, right? Go back to the 1950s and look at the, 6, 7 decades of work. There has been incredible work in taking, so first of all, when we write down these equations, so I'm writing them here in conservative form, but there is a ton of work in asking the question, what is the form of the equations that are more appropriate for a numerical simulation? And by the way, it's not just about computing efficiency, it's especially about stability, mathematical stability. And so, for example, right, there are methods that will work in entropy variables. There are formulations that will discretize the primitive form versus conservative form. So I think it's a good question. I think we have forgotten our history. There is a ton of work that has asked very deep questions about the problem and what the problem should look like when it gets discretized and comes into the computer. We seem to have forgotten that history and gone into this mode where it's like, oh, let's just pretend we don't know anything, and magically we're going to get all these observations, which, by the way, good luck actually trying to generate experimental data from something like a rotating detonation rocket engine, because I talked about the challenges of computing, the challenges of observing. I mean, I don't know where people think these observations are going to come from in the real world. We've gone into this mode of let's pretend we don't know anything and then just keep pushing the button until the hyperparameters get to the point where we match what we think we're seeing.
Doesn't work like that.
Right. To go back to the inside out and the outside in view, if we could bring those two worlds together, we could do so much more. Yeah. Yes, they're old, but
there are a few.
But they're not. They're not. What's the word? They're still relevant. They're not irrelevant.
Sure. Okay.
So I want to sort of pick a little bit of a fight around the machine learning characterization here. I guess if the aim is to recover the physics of a particular system like this, then I absolutely agree, and it's great to see all the pod mode stuff and actually making that useful, and that's really awesome. I guess what I would say is driving a lot of the machine learning deployments for us on an operational side is where we don't have to do the physics quite so much. The things that we want to predict maybe are not, like we can't write down these equations and find a reduced order mode, right? It's where am I going to see the flood hitting my bridge? Maybe yes, in theory I can write down all of those equations, but I just want to predict the impact, right? Rather than the detailed kind of physics all the way through. So I think there's a little bit of a sleight of hand that you're doing there in terms of your outside in and your inside out that sort of says we are going to assume from the start that we care about the physics. And I don't know that that's always the case for some of the predictive things that we do in the real world. But I'm just interested in your thoughts on that as to whether you think that's a sort of an acceptable criticism or not.
Yeah. I mean, of course, the answer is always it depends. And one of the things actually we called out in the Digital Twins National Academy's report was this notion of fit for purpose. It relates a little bit to Nicholas's question as well. Whenever you are going into solving a problem, you have to always ask, like, what does it mean to solve the problem? What am I looking for? What do I actually need to be able to predict? How much confidence do I need to have in the prediction? Do I really need conservation of mass, momentum, and energy or not? And, I think just even asking those questions is super important. I hear you, and I know you sort of live in a world where it's more the data simulation applications, and so you do have the real-world observations, which in some way I would argue those are the things that are bringing in your physics and are keeping you on the manifold that obeys the laws of physics because you are, constantly sort of, balancing in with your observations. In this kind of setting where we're talking about, design, and, as I mentioned, we really don't have the physical observations. The model is really the only thing that can tell us, are you then going to come up with something that is your best guess of an engine that actually is obeying the laws of the universe. But yes, I totally do agree with your point that sometimes maybe you don't have to embed the physics and you can predict what you want without it. But then I would always ask the question, how are you going to know? If you don't have the manifold given to you by the laws of nature, how do you know whether you're on it or off it? And if you're doing data assimilation and you constantly have observations that let you correct your model, I don't know, it's almost like a child on a bike, right? If you constantly have those training wheels, you keep them on track. But if you've got no training wheels, how do you know?
Emily?
Yeah.
So thank you so much for your talk. I especially appreciate the thinking about the conservation of mass, momentum, and energy, which is something that we've thought about quite a bit under one of my projects. My question to you is, what we've found is that the simulations can do a pretty good job of doing that conservation, but once you do that downsampling, like that, any conservation is completely destroyed, and then you train a model on that downsampled data, and it's even further away from conserving anything. So I guess my question to you is, have you looked into that? Do you have any thoughts on, is there any chance of recovering it when you have to downsample as much as you do?
No, this is a great question. And actually, just to sort of take Jess's side for a little bit, I talk about conservation of mass. The reality is the moment you discretize something, these conservation properties are only holding in some, discrete. And then when you go to the reduced order model, it's a weak enforcement. So at any particular point, you're not going to recover conservation of mass. So this is it's actually a really, really deep question. And this is also where I believe the connection with the domain scientists is so important. And this also relates a little bit to Jess's question, which is working with the combustion experts and asking, what is it that you care about? What is it that you really care about? And this comes back to this idea of fit for purpose. And you'll see that in different communities, people will get so worked up if a model doesn't obey certain properties, but then there are other properties that they're willing to just sort of sweep under the rug. And when you really dig into that, it might turn out that there's a certain part of the physics that is really quite essential to the way, for example, this rocket engine works. And so this is where I believe it has to be a partnership. And the answer may be that you still reach for a neural operator that abstracts away a lot of the details of the governing equations. But even to ask the question, what are the variables that you should be working in? I don't think we have those close partnerships between those doing the algorithms and the domain scientists. But yes, I have certainly been in talks where people will get very upset that I'm not actually really conserving mass or momentum. So yes, it's a really good point. Yeah.
Hi, Karen. Thanks for the presentation. I really appreciate it. I'd like to ask a question about the training data. Do you generate it using forward simulations? And the side question is, how much of which proportion of the simulation do you need to do to kind of fit your reduced model? Yeah. Meaning, if you have to run the simulations to get your model, then, how do you get there?
And just to amplify that a little bit, this question of amortization is incredibly important, because if the goal is to only run simulation with the reduced, and you run that simulation to derive the reduced order model and then you declare success, that's absolute nonsense, right? You have to be able to amortize the costs of the training data, meaning that the reduced order model has to be executed many times over different parameters, including parameters that you didn't train on, or it has to be running in real time in some kind of, a digital twin or optimal control. I had it as the very last bullet. There are so many research needs, I believe, around training data. I emphasize the cost, but another one is the question that you're asking, which is how much is enough and how do you know? With these combustion problems, the way it goes is the Air Force they would send us, thanks to Dan for actually figuring out some way that they were able to send us this data, which, by the way, I don't even know how you did it. You and UNIT did that. But they would send us like 100 snapshots, and then we would do all this, and we're like, that's not enough, can you run some more? And then they would keep running, and then they would send us a few more and a few more and a few more. So how many are enough? The answer is how many resources do you have? Because I will take everything you can possibly generate. That is a really unsatisfactory answer, sort of from a more of a mathematical or predictive way. I can tell you, maybe next year, if Nicholas invites me back, one of the things that we're working on, and actually we haven't done any really large-scale problems yet, but we have some really great results on simpler problems, is if the goal is to get a reduced order model, which, when I showed those contours, you already see that the reduced order model is not capturing the high-frequency spatial variation. It's getting the low-order behavior. So do you really need to generate all the training data on a high-resolution grid? Or could you offload some of the training data to a lower resolution grid, knowing that then you're going to introduce some bias into the training data, but then it turns out there are statistical methods, in particular something called a control variate, that if we put together a few samples from the high-resolution grid together with a lot of samples from a much coarser grid, we can actually do that in a way that accounts for the bias. And so we have a formulation for computing the low-dimensional subspace using like a hierarchy of grids. And I think these are the kinds of research ideas that need to make their way and eventually get to large-scale problems to be able to ask and answer these kinds of questions.
Chris.
Great talk. Hi, Karen. Great talk. So I can't, and I think my question sort of follows on a little bit from what you've just been talking about there. I can't help but translate from aerospace into my pet domains, weather and climate. And so we're working with a lot of people who are taking the digital twin, the neural network approach, particularly with the idea of reducing the computational cost of doing a forecast, doing a prediction. But the challenge in there is that the neural network tends to sort of average out the climate effects, and we don't really care if the weather forecast says it's going to be 18 degrees or 18.1 degrees. What we care is if it's going to be -2 or +40 or whatever. So it's the neural network approaches tend to dampen down the extremes in the probability distribution function of variables. So is that a similar case for reduced order models, or how would you get around that?
So it could be. So I kind of glossed over the details of mathematical formulation, but we have what a machine learning person would call the loss function, right? So ultimately, we're solving a minimization problem, saying, find me the reduced order model that best matches the training data's representation in this low-dimensional subspace. And so within that formulation, you have an opportunity to define what do you mean by best. And so we have done some work where best can be, just to average over all the snapshots, assuming that all the parameters, are equal, and your goal is just to find the best fit reduced order model. But you can also say, actually, what I really care about are worst case conditions, right? I care about places where the engine is going to be close to the edge of stability. And so in that loss function, we could weight things in a different way. Now, again, it starts to become a little bit empirical, but this is also where domain expertise and designer intent come in. Another way this plays out is that, and it goes back to the earlier question, not all the variables are equal in how important they are to the designers. So, pressure and temperature seem to be very key considerations, but then density, which according to the governing equations, these are all state variables and they should all be kind of as important as each other. So that's another way you can say, I prefer that you are matching the pressure more than you are matching the density or the specific volume. And that gets you to a different reduced order model that has different properties. So I think this is a place where bringing in the domain expertise. One of the things I don't like about the neural networks is there are just too many knobs to tune, and I feel like you can get whatever answer you want. And the reduced order modeling approach, we have a few knobs, but we don't have nearly as many knobs. So we have 24 degrees of freedom, and we have a few hyperparameters in the learning problem and then this weighting, but we have fewer knobs to tune. So I don't know if I'm really answering your question, but yeah. Yeah. Loss function, but then how you set it, and then how you validate on the closed loop, I think are largely open.
Patricia.
Thank you for your talk. I'm a hardware person. I'm totally at the low level, so I'm going to ask you a question that I don't know if.
Okay.
So we're looking into ways of doing computing, alternative ways of doing computing, and one of the things we're looking at is on physics-driven computing. Where we could do the computation with the physical properties of the devices. So one of the things we're doing is, one of the things we're looking at is partial differential equations, and how can we solve these partial differential equations with these weird computing fabrics. So I guess the question I wanted to ask you is, if you can imagine a perfect hardware platform to solve these kind of problems and to solve the math that you're doing, how would that look like in an ideal scenario? Okay,
that's an interesting question. So I probably know a lot less about hardware than you know about my algorithms. For these kinds of problems, I don't know, but I guess just the analogy that comes to mind is when people talk about quantum computing as being a natural place to do quantum simulations, and it's almost like the hardware mimics what it is you're trying to solve. I don't know. Our colleague Omar Gattas, who was here last year, likes to say that he has the perfect Navier-Stokes simulator, which is he turns the tap on. And he just sort of draws this analogy when people are talking about quantum computing. I don't know. I don't know. I haven't really thought about it, and I'm not sure that I have the skill set.
To win the Gordon Bell
was
Award.
enough for him to win the Gordon Bell Prize, yeah. So I do think it's an interesting question, and it ties a little bit to where Nicholas started, right? Where he asked the question, like, these are the classical equations, and we've sort of got all these methods for solving them. Is this really the best we could do? Again, at the risk of saying something that everybody in the room is far more expert than I am, even if this exists, it doesn't seem that that's the business case that's going to drive future hardware developments in the future. There's just not enough money to be made off conservation of mass, momentum, and energy compared to modeling other things in our world. And honestly, this deeply concerns me because the infrastructure around us is
failing.
It's fading, but it's only here because of these kinds of computing capabilities, and I really fear that we're on a path to losing that, and then you have to ask what is our world going to look like in 20 years if we can't do those kinds of simulations. So it's something that I worry about.
Jason.
Yeah. So I'll make right here.
Oh, there you are. Yes, Jason.
So yeah, to piggyback on Patricia's point, yeah, I mean you're clearly thinking still in terms of the von Neumann model, right? So hardware acceleration, if you can find an economic impetus to it, and then if Moore's law is going away, which it sure seems to be, then where's the low-hanging fruit now? It might not be very low-hanging, but do we have a choice? But that's sort of just piggybacking on what Patricia said. My own point was to try to narrow it MOR down. You talk about space down sampling and time down sampling, and I sort of understand MOR as sort of variable down sampling. Is that a fair characterization?
Yeah, these high fidelity models, you start with a set of partial differential equations, and then typically you lay down a grid and you discretize very finely in space. What the MOR, the model reduction methods are really doing is getting a data-driven global basis that's defining a low-dimensional manifold or low-dimensional subspace and then writing the equations in that low-dimensional space. So it's like a variable transformation, but it's one that goes from millions of very local degrees of freedom, like you would have in a finite element or finite difference method, to just a handful of global degrees of freedom that are defining this low-dimensional space. And the low-dimensional space you've discovered because you had the training data that says, you can get 90% of the answer by just considering these 24 different directions.
So I suppose I would define that as variable-based space down sampling. Is that fair?
Yeah, you could, but it's not, I wouldn't call it downsampling. It's not like you're picking this point and this point. You're actually saying this point and this point are correlated in a particular way so that rather than letting them move independently, I'm going to define this global function and then let that move. If you can remember back to your undergraduate classes in eigenmode analysis, right?
When were those?
I mean, think of these as kind of like eigenmodes, and you're only going to allow a handful of them to vary because you're exploiting correlations in the fine scale structure. Yeah.
All right, fair enough.
Yeah.
Andrew.
Yeah, thanks, Karen. Great presentation. I really like the fit for purpose comment on the digital twins. Get that a lot. My question is, with everything you presented on reduced order models and how you're looking at applying models, machine learning through a lot of this. Well, look, the physics really matters in all this. Like literally, it's life and death type things that are happening with this, especially in aerospace and medicine. The question is, what do you see, or what kind of changes are happening at the undergrad or graduate levels to help everyone kind of understand, okay, yes, this is a tool, a capability that can help accelerate a lot of the work here, but don't lean entirely on it because equations from the 1800s still matter.
Thank you for asking this question and letting me talk about one of my favorite topics. So, and I will try not to talk for too long.
I knew that you were coming from this.
Let me just talk about the graduate level. I have many thoughts about the undergraduate level as well, but the graduate level. So the Odin Institute has its own PhD program. It's called Computational Science, Engineering and Mathematics, CSEM. And it's a really unusual PhD program because it's really intentionally structured around 3 pillars: math, computing, and applications. Everything about our graduate program, the students have to do graduate level math classes, graduate level computing classes, graduate level in whatever their science, engineering, or medicine domain is. The thesis has to have all 3 components. The thesis committee has to have, the math, the computing, the applications. So everything is intentional around that. And that PhD program was founded in 1993. We are right in the midst of doing end-to-end review of the program. And there are many reasons we're doing an end-to-end review, but one of the big reasons is so much has changed in the field of computational science. We've been tweaking classes. We have new classes and foundations of data science and machine learning, extra electives in machine learning, but we wanted to take a holistic view right back to the drawing board. One of the things that really makes my heart smile that has come out of that is that the foundations that we have been teaching for, 20 some years, actually almost 30 years, actually, I expected the students to come and say, we don't need functional analysis anymore, just give us machine learning. That did not come out. It did not come from the alumni, did not come from the students, the current students, it did not come from the faculty. So none of the stakeholders, everybody, now you might just say that Odin Institute is a place that attracts people who believe in conservation of mass, momentum, and energy. But for example, that functional analysis came out as being this, and that's what our students take in the math class in the first semester. So I don't know how other places are going. I mentioned earlier the Quran Institute. You might have seen the Quran Institute just merged. They created the Quran Institute School of Computing at NYU. It's going to be interesting to see because Quran is another place where that kind of applied math is so incredibly strong. It's going to be interesting to see if that changes their education. But at least where we are going, we are changing, we are embracing more modern computing, machine learning, and data science. But we are doing that in a way where we still are keeping the foundations of applied math and the physics. And I think that's absolutely essential because, if we lose this, I honestly don't know what we're going to have. I'll tell you what we're going to have is whatever airplanes we're flying today, we're going to be flying on those airplanes in 30 years' time, and it's going to be really unpleasant and probably unsafe. That's right. So I deeply believe we've got to find a way to not forget the old while we embrace the new. And education is absolutely central part of this. So I was just so happy when the student surveys came back and numerical linear algebra and functional analysis, they were alive and well. I thought, oh my gosh, that's a relief for now.
Join me saying thank you to Karen.